Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the binary and hexadecimal number systems. So these are very important because they're used by computers, and computers do pretty much all the work in cryptography these days. So we'll only look at integers in binary and hexadecimal. Okay, so how does this work? Well, let's look at our current number system. If I want to write a number like 32,768, I write it in columns. The rightmost column is ones, then the next column to the left is tens, hundreds, etc. Each new column is a power of 10, and I can keep adding columns as I please. If I want to add more columns to the right, they are numbers less than 1. They're decimal numbers, but we won't be looking at those in this video. So in each of these columns, I need to place one of 10 symbols. In decimal, base 10, which is our normal system, we use 10 symbols, 0 to 9 inclusive. So in binary, the system is base 2 instead of base 10. So each of the columns is not a power of 10, but a power of 2. So we start with ones again, and then 2s, 4s, 8s, 16s, and so on. But in binary, only two symbols are used, 0 and 1. So each column is filled with either a 0 or a 1. That's actually what makes it so attractive to use in computing. Everything is either 0 or 1, 0 false, 1 true. So just be aware that if we have a number like this, we don't want to confuse it with the decimal number 10,110. So in computing, often you will see a 0B at the front of the number to indicate that it's a binary number. If it's just written like in a Word document or something, we sometimes use this subscript 2 to indicate that it's base 2. Either of these is fine. They just help us understand that this is a base 2 and not a decimal number. So this number here in binary, if I wanted to convert it to base 10, the decimal system, that's really easy. I have 1, 2, 1, 4, and 1, 16. 16 plus 4 plus 2 is equal to 22 in base 10. This number in binary, 10110, is equivalent to 22 in decimal. So how would I write a number like 125 in binary? Well, what I have to do is write this as the sum of powers of 2. So it's great if you know the powers of 2. But if you don't, let's go through them. 1, 2, 4, 8, 16, then 32, 64. The next power of 2 is 128. Now, because that's more than 125, I don't need it here. So I need to find a combination of these that I can add up to get to 125. So I'll start with the highest power of 2 less than 125, 64. So I need 61 left. So I'm going to start with the highest power of 2 less than 61. If I add 32, I've got 96. 29 to go. Next highest power of 2 below 29 is 16. So now I'm at 112. There's 13 to go. 8 plus 4 plus 1. So I've written 125 as the sum of powers of 2. So what I'm going to do is I'm going to put a 1 in the ones column. There's no 2s, so I put a 0 there. There's 1, 4, 1, 8, 1 in the 16s, 1 in 32, 1 in 64. I can stop there. So I'll just put a little 2 here to show that this is not the number in decimal 1,111,101. This is a binary number 1111101. All right, let's now look at doing a bit of arithmetic in binary. So when we do cryptography, we will occasionally have to add these called bit strings. They're just strings of binary digits. So these are binary numbers. We'll add them together. All right, let's do it. So this is 1 plus 1 is obviously 2, but in binary, we're going to put down the 0 and carry the 1. 2 in binary is like 10 in decimal. Okay, so we carry the 1, we get 1 plus 1 plus 0 is 2. Put down the 0 and carry the 1. So what do I do here now that I've got 1 plus 1 plus 1? Well, that equals 3. So 3 in binary is equal to 1, 1. It's got 1 unit plus a 2. So I put down the 1 and I carry the 1. 1 plus 0 plus 1 is 2. 2 is like 10 in decimal. We put the 0, carry the 1. 1 plus 1 is 2. So put the 0 and carry the 1. That's our answer here. So let's check if we were right. This top number is 1 plus 2 plus 4 plus 16. The top number there is 23. This number is 1 plus 4 plus 8, which is 13. So 23 plus 13, you know, is 36 in decimal. In binary, that's 132, no 16s, no 8s, 1 4, no 2s, no 1s. We are correct. So you might think it's easier to convert each of these into decimal numbers, and that's true because of the size of these. But when you do cryptography, sometimes you'll have a bit string that's so many digits, converting everything into base 10 takes too long. All right, let's now look at finding how many bits we need to represent a number. So in binary, the numbers are represented as a string of 1s and 0s. Each individual 1 or 0 is called a bit, which is short for a binary digit. So we're going to figure out how many bits would be required to store the number 100. I can assume that this is a base 10 number because there's no subscript there telling me otherwise. So it really helps if you know your powers of 2. So 64 and 128 are the powers of 2 on either side of 100. So let's look at those numbers. So 64 is 2 to the power of 6. So it actually has 7 bits. It's 1 followed by 6 zeros. That may seem strange, but that's exactly how it works in base 10. For example, 10 to the power of 6 is 1 with 6 zeros in decimal, this number being a million. 10 to the power of 7 in decimal numbers is 1 with 7 zeros. So in decimal notation, we have 10 to the power of 6 is the smallest number with 6 digits. 10 to the power of 7 is the smallest number with 8 digits. Anything between these two numbers, more than a million but less than 10 million, it will have 6 digits. But remember, in binary, we basically are replacing 10 with 2. 2 in binary is like 10 in decimal numbers. So 2 to the power of 6 has 7 digits. You can probably guess 128, which is 2 to the power of 7, will have 8 digits. It will have a 1 followed by 7 zeros. This is what 128 looks like in binary. So 2 is like the 10 in binary. Any number between these will also have 7 digits. In binary, we call those digits bits. So 100 in binary will require 7 bits to store. In fact, in binary, 100, we have 64, 32, no 16s, no 8s, 1 4, no 2s, no 1s. You can see clearly it has 7 digits in binary. So that was a bit of an easy example because 100 is a small number, but for something like 10 to the power of 60, it's not a small number. We're not going to be able to figure out the 2 powers of 2 on either side of this. What we can do is use this rule in our index laws. We want to write 10 to the power of 60 as a power of 2. So 10 to the power of 60 is 10, which is 2.32 blah, blah, blah. to the power of 60. Using our index laws, power to a power rule, I keep the same base and I simply multiply together these two numbers. So multiplying them together, we get 2 to the power of 199.31, blah, blah, blah. We don't care that much about that. So that helps us. The two powers of 2 on either side are 2 to the power of 199 and 2 to the power of 200. This is the smallest number in binary that requires 200 bits. This is the smallest number in binary that requires 201 bits. So it's like we're rounding up. This will require 200 bits. If we were to write it out, and I'll never ask you to do that, but if we were, it would have 200 digits. The first would be 1, and then there'd be a sequence of zeros and ones. All right, let's now look at the hexadecimal system. So hexadecimal is base 16. Now computers sometimes store numbers in base 16. So why is that? Although binary is really easy to work with because you can store a 0 for something false and a 1 for something true, it's nice and easy, but as you just saw, it requires a lot of digits. There's a lot of bits that are required to store the numbers. In hexadecimal, we only require a quarter of the digits to represent the same number. That's because 2 to the power of 4 is 16. So we can represent larger numbers using fewer digits. So, as you would expect, when we have a number base 16, the columns are powers of 16. The first column is still units, the next column is 16s, or 16 to the power 1, and the next column is 16 to the power 2, or 256. So in binary, base 2, we had 2 symbols. In decimal, we had base 10, we needed 10 symbols. But in hexadecimal, we need 16 symbols. So how do we get around that problem? See, we can't write 10 as 10 in hexadecimal because that is the number 0 ones, 116. 10 in base 16 is 16. 10 is how you represent 16 in hexadecimal. So we need another symbol for 10. So whoever just decided we're going to use little a for 10 and B for 11, all the way up to F for 15. We now have 16 symbols. 0 to 9 work as they normally do. That's 10 symbols, and we have these 6 symbols here. So if I want to convert this to a decimal number, so I would have 3 ones plus E. Now E is equal to 14, so there's 14 in the 16 column. And as we said before, A is 10. We have 10 in the 256 column, so it'll be 10 times 256. So you can just put that on your calculator. That is the number in decimal, 2,787. All right, let's now look at going the other way. So we're going to convert 1200, a decimal number, into hexadecimal. So how do we do that? Well, we know that 1200 is between 256 and 4096. So we're actually going to need 3 hexadecimal digits to represent this. So we just have to figure out which number goes in each column. We need to figure out how many lots of 256, how many lots of 16, and how many lots of 1 can be written. Okay, let's start with the highest power that is less than 1200. That's 256. If we do 1200 divide 256 in our calculator, we end up getting 4.6875. Really what we're interested in is the 4. 256 goes into 1200 4 times, and there is a remainder. So what is that remainder? Well, 1200 minus 4 times 256 is equal to 176. That's what's left over. So how many lots of 16 is that? Well, 176 divides 16 is 11, and there's no remainder. So I need to put 11 in this second column, but hang on, I can't do that. I can only put one digit in each of these. Remember that instead of writing 11 in this column, we write B. Now, because there was no remainder, no left over, this will be a 0. So in computing, we usually write a 0x at the start of a number to indicate that it is a base 16 number, or when you're writing it like in hand, you might write a subscript of 16 to let you know this is a base 16 number. So this is an improvement. If I wanted to write the 1200 decimal number in binary, I'd actually need 11 bits. So hexadecimal has the drawback that you need a lot more symbols, but you need fewer digits to represent the same number than you do in binary. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.